So here's homework 6, problem 1 in dynamics. We have a UHart engineering student is attempting to move this box A that's 50 kilograms, and it's up a slope that's 20 degrees, and there's a coefficient of friction, kinetic friction, of 0.4. They're pulling the cable, and that cable makes a 15-degree angle with respect to that slope. And he is pulling at 400 newtons. So the tension in the cable is 400 newtons. And they're starting from rest. We want to find the velocity of the box after it has moved 2 meters beep, up the slope. Okay, so I kind of went on autopilot and started solving this after I had written out the problem statement. So I erased it so that I could make it for this video right here. Because we want to go step by step in here. And I just finished my first ream of paper there after about a semester, 2 semesters? No, I don't know. I just went down to the bookstore and bought, how much did it, I think it was $10 for how many sheets? 200 sheets. Yeah, 200 sheets there. I bought 2 of them. I spent $20 plus tax. But it lasts me a really long time. So I've done a lot of problems on this. But anyway, so we go. So here is the problem statement written out. First thing you want to do is the most important tool in our toolbox, the FBD. And we've just learned that there's got a brother named the IBD. Not irritable bowel disease. I don't know. No, it's the inertial body diagram. And because this thing is on a slope, it's going to make it our lives easier to make a coordinate system that is matching the slope. Here you go. So I like to call these x prime and y prime. Don't worry, we don't have to do a coordinate transformation. That'd be an interesting thing to do though. But anyway, we're going to do the FBD over on this side. And I'll try to draw the same box in both places. I don't know how successful I'll be. We say it's going to be equals to that, right? And something like this right here. So much easier to do this on a computer, isn't it? All right. Does it look like about right? I think this one's a little higher than that one. Doesn't matter. All right, so we start applying on the FBD. Let's look at the forces that are happening onto this. Okay, I like to go with the normal force is F here, so I'm going to call that F subscript N. The box is going upwards that way, so friction is going in the opposite direction. Right there. So there's F, F. Let's make the weight is going to be there, right? It's vertical. Gravity's always working down. But there should be like maybe a dashed line. Kind of says that's the angle, and this right here is going to equal the slope, and you can work out this to your if you don't believe it, right, you could go, if you go these things, whoop, you could see that they're going to move at the same angle. That's one way I would test it. We're also going to have a force, right? So here's the force, here's the line, I should say, that's in line with the slope. Here is the force of the tension, FT. I forgot to label this one. I'm going to call this MAG because I already was using symbols everywhere. I just went ahead and put it there. But this is the weight, right? Mass times gravity. Over here on this side, this is where we get the acceleration, and it's only going to accelerate up the slope, right? It can't pass through and it can't jump off. So therefore, going there. So this is MA, acceleration A. That's all that belongs on the right hand side. And now voila. So what we do here, this is very typical of a friction type problem here. We're going to do in the y prime direction first because we want to get that normal force. That normal force is not equal to the weight, and it's even less than just taking it by the angle right here. It's also this force of this tension is actually kind of lifting the box up a little bit. Don't worry about tilting and that kind of thing. That's rigid bodies, right? This is just a particle, even though it might look like it has shape. The shape doesn't matter. So we take the sum of the forces in the y prime direction equals mass times acceleration in the y prime direction. Right? This is the sum of the forces, mass times acceleration, right? So this diagram matches that equation. Now, I like to draw my arrow right there with the plus, right? But I kind of made it a little thing. And we also know that it can't accelerate there. So the sum of the forces in the y prime direction is actually in equilibrium in that direction, equals 0. So I'm going to start here. Let me start with Fn. It's nice to start with something positive. Fn is upwards. Plus, let's see, there's going to be a portion of this, and I think that needed to have, there you go, I'll put the angle in there, that beta. So there's also going to be an Ft, but only the sine of beta portion of it. And then we're going to have, this is going to be down negative. It's going to be in the negative y prime direction. But that's going to be MAG cosine of theta equals 0. Fn is the only thing we don't know here, so we'll go this 400 times the sine of beta, which is 15, minus my 50 times 9.81 times the cosine of 20 degrees equals 0. So we can get our Fn is equal to, calculator out, and let's see, 415 sine times, okay, and then 50 times 9.81, boom, times 20 cosine times, subtract out, that makes sense that it's negative because it's going to go over to the other side. So that ends up being 357.4 newtons. Now we can find out the friction because this is going to be mu k times Fn, or 0.40 times our 357.4. So that's 143.0 newtons. All right, and now we have the sum of the forces. I'll just go shift over here a little bit. Sum of the forces in the x prime direction equals mass times acceleration in the x prime direction. Positive is up the slope right there. And so on the left-hand side, we're going to have negative F, right? We're going to have a negative MAG, but times the sine of theta. And then we're going to have plus Ft times the cosine of beta, and that's everything. Fn doesn't have any x component, and then it's all going to be equal to the mass, I'll just keep it as this, times the acceleration of a. And we know everything except for the acceleration a, so we can just find it. So we'll say that it's a negative 143.0 minus my 50 times 9.81 sine of 20 degrees plus 400 times the cosine of 15 degrees equal to 50 times the acceleration of a. And hopefully it's a positive number, otherwise he's not pulling hard enough and it's just going to go downhill. It doesn't actually make a lot of sense because now the friction has to go the other direction. But let's not worry about that. Let's have faith that we pick the numbers randomly correctly. So let's see, I'm going to add that 59.81 times it times 20 sine times, so those two are combining. Okay, I think it would be okay. And we have our 400 times 15 cosine times, just enough. It got close. Like all of this right here was like 386.4. No, this was 386.4. All of this was 310.7. So it just, there is still a net force going upwards right there, and we needed that. Okay, so we divide that by 50, and we get 1.513, and this is meters per second squared. And anytime you get an acceleration, there's always an acceleration you can compare it to, right? Boom, right there, right? You could picture that acceleration maybe. Well, you can kind of figure out in terms of the amount of G's, the amount of gravitational things, and so if you think of just gravity is close to 10, this is like 1.5, right? So yeah, we can kind of picture the things. But now we got to figure out, we're actually looking for the velocity, and we're asked about a velocity up the slope. I went ahead and called it S. Right here, I just call that dimension S. Why not? I don't know. And so if you get the velocity, it's going to be equal to the original velocity plus 2 times the acceleration times the change in position. Right? This starts off at 0. So we get V squared is going to be 0 plus 2 times 1.513 times 2. And we will find the velocity, so we really just multiply it by 4, right? 4 times square root. And we get that it's going to be 2.460 meters per second. So let's write that answer out again. All right, let's see here. Let's move that down instead. So the answer, V is equal to 2.46 meters per second, and they asked for velocity. Let's double check. Asked for velocity. Determine the velocity. Just trying to make sure that you guys remember velocity has direction. So it's got to have a direction. It's got to have a hat on it, and it has a direction. And what's the direction? Well, it's going to be going that 20 degrees up there. There you go. Oh, let me box it. Where am I? There it is. Boom. Voila. Problem done.